I say basically the inside, I think wanted you know this, the inside the home, the system consists of a cooling coil, a fan, and a heating section where it applies, and a filter. Then the outdoor portion of the unit houses basically the condenser and the compressor. This makes us to understand that on the indoor unit has a cooling coil, which is like if you, I know you guys might have seen, maybe some of you might have seen a situation whereby they opened an indoor, maybe for services or maintenance. But one thing I want to relate to easily, many of you would have seen refrigerators. You know, there's a way they run copper pipes in refrigerators. You might have seen something like that. That is almost like the same way because it's not, I know very well, it's not everyone that would have had that chance to be around maintenance of air conditioning indoor units. That's almost the same way the light films across the space. That's the same way it is done inside the indoor unit. Then it has a cooling coil. Then it has a fan which blows air across the cooling coil. Then we have the heating section in where it applies. The heating section doesn't usually apply in most parts of Nigeria, but in cases that are that has very low temperatures, maybe in places like Calabar and some other places, in some other, I know quite well in some hotels that we've been to, we know that they use heating instead of cooling. But in most parts of this temperature, we do a lot more cooling. Then we have filters. Filters are basically filtration mechanisms which prevents dust and other microbial activities running through your system. So the main part of the indoor is the cooling coil, then the fan, which does nothing more than the job of a fan. But the cooling coil is the connection, stays as the connection between the indoor and the outdoor unit. I hope you get that. Obviously, if you have questions on any of these things, you can actually put up those questions and we can address them as we go on. Then now, I'll talk about the outdoor portion of the unit. This is the outdoor portion comprises of the condenser and the compressor. The compressor is actually the workhorse of the unit, the main the powerhouse or the powerhouse of the air conditioning system, because it's the one that does the compression of the gas and makes it run through the copper piping into the indoor cooling coil, then back to the compressor. I have a short diagram which should be able to explain a little more in that regard. But one thing I want you to see here, this is an example. I hope you guys can see my cursor. We have the indoor unit, then we have the outdoor. Then in some cases, as we have this split, in other kinds of split systems, there's something we call multi-split systems. This is a single split system, but this is just for information. This is a multi-split system in which you can have a single outdoor to take care of one outdoor. You see the refrigerant copper piping taking care of one outdoor. This is a cassette system, and this is another indoor type. But the truth of the matter is the capacities of these items would be required for you to actually get what you need in terms of the size of the outdoor. I hope you understand that basically. These are basic explanations, and these are basic illustrations on the split system. I will use this layout to explain the air conditioning process and what we just explained about the split system. I just want you guys to follow me as much as possible. Then if you have questions, we can bring back the questions later. If I would put, okay, I will start from up here, where we have, you see the coils, I think you can see the coils. These are the copper pipes running through coils, running through an accessory expansion valve, then the same copper pipes all the way to connected to the compressor, then the same copper pipes running from the compressor, which onto the condenser, then back to a desiccant dryer, then back to an expansion valve, then back to the evaporator coil. The light blue or sky blue, for most of you that attend wages very well, I don't know what this one is. This is deep blue. I know this is navy blue, but I know they have sky blue, they have turquoise blue, and all those waiting blues. Whatever blue that this one applies to you, just pick it. But this is blue for me. This is navy blue, and this is blue. This navy blue is defined as a low pressure refrigerant in liquid form. Let me explain that before we now go around the whole sequence. Then the light blue is a low pressure refrigerant in gas form. Same also light blue. Then the red is a high pressure, high temperature refrigerant in gas form, which is this very thick red. Then if you look at the one that is almost changing from red is like going to amber, then back to yellow. The yellow is a high pressure, high temperature refrigerant in liquid form. I hope you understand lightly. So what is being explained there is the thermodynamic process that occurs within the system. This is like this is the main refrigeration system, basically. What we have mainly through this line is refrigerant, but I think I might just mention at this point, there are various kinds of refrigerant gases. We've got R22, which is what is mainly being used in most air conditioning systems now. Most residential air conditioning systems at the moment. In some cases, there's an improvement of going from R22 to R410, then RA32, and the rest of it. But mostly, what is being used in space system now, you see R22. In some other cases, you can see R410. For some of these technologies and this improvement comes with a different bit of cost. So let me just run through this. Let's start from the compressor. The compressing unit, which is the main workhorse of this system, compresses the refrigerant gas from basically, let me just say, from low pressure gas to a high pressure, high temperature refrigerant in gas form. So what happens is it compresses it and improves, through compression, just from thermodynamics. If you compress, you get more in temperature. You have an increase in temperature through compression. So from the compression, it pushes the refrigerant gas through the discharge size of the pipe. You know there are two pipes that are usually connected in AC units. There's a larger one, there's a smaller one. It pushes it through the discharge pipes of the pipe, then runs it from that point through the condensing unit. This condensing unit is simply the outdoor. I hope you understand. This is the outdoor. Okay, let me put it like this. This is the outdoor point, and this is the indoor point. The condenser, which has a condenser fan, is actually there basically to blow air across the condenser coil to drop the temperature lightly. I hope you understand. And after compression from the main unit, which is the compressor, the refrigerant runs through the condenser coil, then the condenser blows air across it to drop the temperature, and it will still be at high pressure, as said. It will still be at high pressure, but the temperature will drop, and it will come from the gaseous form into a liquid form. It will run after that point into a dryer. The essence of this dryer, this desiccant dryer, is to allow for proper refrigeration and to take out any form of moisture in terms of water or oil, whatever it is that is actually within the refrigerant, which can actually damage the system or which can actually drop the quality of improvement of the system. It runs through the dryer, then runs from there to an expansion valve. The essence of the expansion valve mainly is to drop the pressure. I hope you understand. It will drop the pressure from high pressure down to low. And at that point of that drop, it comes still stays at liquid, it still stays in liquid form, which runs through down to the evaporator coils. Then this is what happens in the evaporator coils. Through the evaporator coils, the pressure of the gas is still low, but it's still in liquid form. Then the fan in the evaporator blows air across this and blows into the space. That is why you have that cooling you have, because the cooling coil the cooling coil in the evaporator receives the refrigerant gas at low pressure. And when it does, at low pressure, it blows air across it and pushes the cool air into the space. Then, and when you have loss in terms of cool air, the phase will change from liquid then back to gas. Then when it does, it goes back again to the expansion valve, which drops the pressure a lot more before it gets back to the compressor. So the cycle keeps going back and forth, back and forth, back and forth, back and forth as such. That is why in all, you will know that at high temperature and at high pressure from the compressor, when the refrigerant runs to the evaporator, that is where you have, because in most cases, most outdoors, you will see that it is blowing out heat. I know many of you would have experienced that it's blowing out a lot of heat at different times. So that is why you have, because the compressor is pushing the refrigerant through the cooling coil at very high temperature and a very high pressure. That's why you have the heat being blown out at this point. Then the reverse of that, which is what happens within the evaporator line on the inside of the space. This is still the same, if I would say, it's still the same concept that comes around from single split to multiple splits and also to large centralized air conditioning systems, because this is the basic of refrigerant systems. Now, the thing there is, in most other cases, you have various cross-sectional areas of cooling coil for evaporators, and also various cross-sectional areas of cooling coils for the condensers, and various capacities of compressors, as the case may be. But I will move on to the next page. I'll move on to the next page now. I'll move on to the next page now. We'll talk about, like, I hope you guys understand, have a brief idea of the refrigeration system now from that former page. We'll talk about some design requirements. We cannot really go into this in full, but I'll pick each of these things and explain how it applies, because if we really want to go into it in full, it has to be a much more robust training as it will be. One, design requirements in air conditioning. Design requirements means the things the things you would consider for you to do a proper design for an air conditioning system, whether you are doing it in terms of capacities required, or the nature of the system you are applying, or in nature of installation you are looking at. Those are some of the things. These are some of the things you would really need to work with. These are some of the considerations you will put into thought, and these are some of the these are some of the how would I put it? Some of the basically design considerations that you will actually apply for you to actually get what you want in terms of the end product, in terms of the capacity you intend to achieve for cooling and for installation. One, we have building application. What building application means is, we have different kind of buildings. In concept, we have residential buildings, we have office buildings, we have industrial buildings, we have hospitality buildings. The application of the building, then we have other, maybe we can use them, get them as convenience buildings. Then we have what application would I put? We have convenience buildings. Then I'm trying to pick out something for some other type of, yeah. We have what should we call them? Yes, we have event buildings. We have event buildings which require very large number of people at different kind of time. Then okay, let's call it congregational buildings, auditoriums, and the rest of them. What we do in terms of building application is this: building application for design would actually make you understand the nature of cooling you require and the nature of system you need to apply for that building, whether it's residential, whether it's commercial, whether it is industrial, whether it's congregational, as the case may be. All these natures of applications requires different design thoughts, requires different design specifications applications as it applies to air conditioning design. Then we have building location and orientation. The north, south, northwest, and the cardinal representation as it may be. These are some of the other items that needs to be considered in terms of that as well. Then we'll talk about physical dimension of space. The spaces you require is also a very important thing. If you're using a large space, you need to know the size of space you're dealing with for you to have an average estimate of cooling that you require. Is someone saying something? Okay. You need to know the kind of space you're dealing with for the kind of cooling you require. Then we have building material types used. Then we have things that has to do with relations with windows, walls, and types of wall materials. We have different kinds of wall development materials these days. Apart from the normal masonry blocks, we have full solid block walls. We have plaster. There's a lot. There's a lot in terms of considerations for air conditioning design requirements. Then we have this coming up a whole lot more. Now we have the dry walls. We have dry walls with insulations, dry walls without insulations, dry wall with sheetings, dry wall without sheetings, and how all these items apply with transmission coefficients and heating coefficients and the rest of them. So these are some of the things that need to be looked at. Then we have building loads. I know a number of you might have heard of sensible heat loads, latent heat loads, the difference between those loads and how those loads apply in different application systems for human loads, for equipment load, for building load, for orientation load, and the rest of it. We have heat load generators, then others. Because heat load generators are various kind of items that develop various kinds of heat within your space. Then we have surrounding load conditions, the conditions that actually apply, that affect your unit. Because let's talk about something. If you have a space that you're trying to cool, for instance, and you discover that the space is built with 50% masonry block and 50% glass. Your conditioning design will have to be different. If the space is built with 75% block and 50% glass and 25% glass, your condition will have to be different. If it's done with a 2.5, let's say, for instance, let's say a 1.5 square meter window space, and the rest is what? Your condition space will have to be different. If the orientation of that building, of that unit of space, is facing the westward side of the coordinate, or is facing the north-south side of the coordinate, your design conditions will have to be different, because those are some of the things you need to consider for you to understand fully what kind of load generators you have right about your system and your place. Then we have the typical outdoor conditions, which is something we can't just go into now because it's voluminous and large. Then we have indoor conditions among the host of other requirements that we need to consider for you to have a proper cooling. But one thing we will try to focus mainly, which is in terms of the light calculations we will just play with, is averages. We'll take averages, then we'll look at based on thumb rules, just to make it very streamlined. But I would need to say that at different points, there is a lot in terms of air conditioning design and air conditioning design applications. Then also the design requirements. The design requirements and design system based on the first principle of air conditioning is actually very large, very wide. But something one would always need to get very familiar with for you to know the kind of engineer you intend to make yourself to be. So I will come down to basic split terms in HVAC system. I hope you can still see my slide. So one thing which is extremely important in air conditioning is split air conditioning is specification. Then I would introduce you, for some of you that might not be very familiar with British thermal units, and some might be familiar with it, British thermal unit. British thermal unit is the unit of specification, mainly for most air conditioning, for most split air conditioning systems. Some will specify them in kilowatts as well, and some will. Most cases, it's not very professional in specifications of HP, horsepower, and the rest of it. But in most cases, for a layman who are non-engineers, many of them are really familiar with horsepowers and the rest of it and all that. But for those who intend to be pure, well brought up, well defined engineers, it will be ideal for you to understand the the intricate parts of the design process in itself. One, we'll talk about the British thermal unit. We look at the approximate heat required to raise temperature of 1 pound of water by 1 degree. I hope you understand this. It says the appropriate approximate heat required to raise the temperature of 1 pound of water by 1 degree is like saying we're increasing the temperature of a pound of water from 50 degrees to 51 degrees, or we're moving it from 60 degrees to 70 degrees. It's just like a simple example. Most times in liquid flow and solid flow, let me put it that way. Most relations are done in terms of size and time. I hope you understand. Most relations are done in terms of time and size. It either is done in terms of size, in terms of size by time, or in terms of size by temperature it may be applied. But with this, we'll be doing it in terms of size by temperature and also by time. Now, from this, if you look at this, it says British thermal unit is the approximate required to raise temperature, like I said, of 1 pound of water by just 1 degree Fahrenheit. Then AC units are usually rated in BTU of heat they can actually remove from a space per hour. That is actually, I have tried to streamline this as simple as possible. ACs are specified in terms of usage amount of BTU they can remove. The BTU is British thermal units. They can remove from a space in 1 hour. Other common ratings include ton, then kilowatts. Averagely, if you would understand, you can sometimes we have been some cases where we have air conditioning. They'll say this is 5 ton, that is 10 ton, that is 20 ton, that's 3 tons. I hope you understand. Some of you would have come across things like that. And some of you, but what we hear mostly across board is usually, even from most air conditioning distributors and retailers, a lot of them would see these units in hospital. I was out to pick up an AC unit some time ago, and I asked the guy selling, the white guy like that. I asked him, I said, I want a 3.5 kilowatt unit. The guy was confused. He was basically confused because what he's used to is either at 1 horsepower or 2 horsepower or 1.5 horsepower and the rest of it. That's what they know. That's what they understand. But for engineers, we usually do not apply the horsepower in terms of cooling. No, it's not done. It's either you specify your specification comes in terms of in tonnage, or it comes in kilowatts, or it comes in BTU per hour. And as we've known now that the specification of the air conditioning is done in BTU per hour. Now, averagely, in terms of value relation, a ton, if you look at this, a ton is equivalent to about 12,000 BTU. Just 1 ton. 1 ton is equivalent to about 12,000 BTU. Then also the 12,000 BTU is also equivalent to about 3.51 kilowatts. That relation is just like A equals B, then B equals C. What that tells me is that A is equals to C. I hope you understand. If we have A that is equals to B, then B is also equals to C. Then in one way, A is equals to C. Then you can relate between what value of A is to C, and I can actually represent B in terms of A and also represent B in terms of C. That's what this relation simply just means. It's very simple. It's very simple and very direct for you to understand that a tonnage of cooling, of the heat of cooling, is approximate, is equivalent to about 12,000 BTU. Excuse me. And also 12,000 BTU is also equivalent to about 3.51 kilowatts. Please note, this kilowatts is in kilowatts of cooling in terms of capacity of compressor. I hope you understand. It's not in kilowatts of electrical light power. It's not in kilowatts of electrical power. This is in kilowatts of cooling. In most split system panels, if you look at the systems very well, you would, okay, I don't have that there. If you look at the systems very well, like the nameplates, I hope you know what we call nameplates, spec plates on either outdoors or indoors. If you look at them very well, you will see the rating, the cooling capacity in terms of rating of the unit in BTU power, and some will also specify it in kilowatts. If you have, okay, let's look at this so I can explain what I want to explain quite easily. For common shelf capacities of split units, you've got 9,000 BTU per hour, which is also equivalent to 2.65 kilowatts, then which is what they usually call the 1 horsepower. Okay, then we have the 12,000 BTU per hour, which is equivalent to 3.50 to 3.51, 3.52 kilowatts, then which is what they call 1.5 horsepower. Then you also have the 18,000 BTU per hour, which is equivalent to 5.64 kilowatts, thereabout, which is what they call the 2 horsepower unit. Then you now have the 24,000 BTU and now, which is equivalent to 7.10 kilowatts, which is what they call the 2.5 horsepower. I hope after this training, this free training, you guys will not call AC, specify ACs in horsepower again. Because doing it in horsepower, you just be like that guy that was just buying ACs and selling them. He doesn't give a damn about what capacities they are or what technical terms that are involved with it. ACs are mainly professionally specified in terms of cooling loads, and the cooling loads is given in terms of BTU per hour and kilowatts. You can actually have it in, and in some cases, in some spec plates, it's either you have them as 2.65 kilowatts or you have them as 2650 watts, which is not in, kilo is 1,000 of wattage. I hope you understand. You can have them as like 265 kilowatts, 2.65 kilowatts, or given as 2650, 2,650 watts, or 3,500 watts, as the case may be. But I need to make you guys understand something. For there are different brands of air conditioning units out there. We've got the LGs, then we've got the Daikin, we've got the Medias, we've got the Chigos, we've got the Breeze, we've got the Yoks, we've got which other Panasonic, we've got which other one do we have there? We've got Panasonic and a host of others. But one thing that actually applies to many of these units in most cases, many of these product brands come in slightly different specs. It comes in slightly different specs, either specs of 2.65. When some have it in 2.65, LG might have it in 2.65, Panasonic might have it in 2.60, Daikin might have it in 2.68. All these things are just slight marketing points in terms of capacities that they designed with. I hope you understand. So you will might most likely not see 2.65 in every unit. Neither would you see 3.50 in every unit across board. In some units, you see them as 3.50. In some units, you see them as 3.54. In some units, you see them as 3.32. What that tells you is my unit Daikin might say 3.32 kilowatts. What they're telling you is that their unit will provide 3.2 kilowatts of cooling. And now, I hope you understand. Others might do. While Daikin is saying, for example, is additional 3.2 kilowatts of heat per hour at a time, Panasonic might be doing 3.7. They are same price, but that you don't notice in some of these units is that if Daikin is 34,000, for instance, Panasonic might now be 39,000. These are few selling points in terms of differentials between all some of the. So basically, fine. Now I need you guys to understand something basic, very basic. Because when you get something free, you will get it free. When you get something free, you will get the free the upstages. But we'll look at the average selection capacities. But it is very important that you do not base all of your understanding on free knowledge. It is extremely important because you see, like we once talked about one of the other things, experience. It's either you experience something or you buy that experience. These are two different things. You can experience. You want to experience marriage. You can, for instance, you can experience marriage by getting married and experiencing it, or you buy the marriage and experience it ahead of time. You can deal with things in different ways. Knowledge spans across time. You need to always try to keep improving your knowledge bit after bit as much as possible. Just keep increasing it as much. We'll look at why I've said that is because I'm going to say something after I discuss this average selection capacity, because there are still some intricate points that we still need to look at in context. Now, there's what we call Tom rule. Tom rule gives you in the industry. Tom rule gives you an average. It gives you an idealistic size, idealistic rating for estimation purpose. I hope you understand. Give you an idealistic specification for estimation purpose. One, if you look at this profile, we have for average selection capacities by Tom Brew, we have about 0.18 kilowatts of cooling heat is adequate for 1 square meter of floor space. I hope you guys can relate quite easily with the square meter. Yeah, you can have some of like people will be able to relate with 1 square meter, and if you can relate with 1 square meter, that is the 1 square meter is the area of 1 meter by 1 meter, which is 1 meter of length and 1 meter of breadth. But I will explain mine in terms of free cubic meters. I hope you understand. If you do not understand this, please put up a question to it, then I will deal with it at the question session. What this means in every space you need. Spaces are defined in terms of floor area, mainly by architects, but for an air person or a mechanical engineer into air conditioning, your spaces are defined by volume because you need your length of space by breadth of space by your height of space. I hope you understand. You need your length of space by your breadth of space and by your height of space. In most residential development, your height of space is usually into 2.8 to 3 meters. That's your height of space. That means, what that means is for every cubic meter of air within that space, okay, for every cubic meter of air within that space, you need some level of cooling to remove that cubic meter of heat within that space at each time. I hope you understand. What this rate, this average estimation gives you of the average range of 0.189 kilowatts of cooling heat is adequate for 1 square meter of space. Please note this, the range does not apply in all applications. It is an estimate. It is an estimate which can still be maybe slightly applicable for single split designs. But when you go to multiple size or more pronounced size of design specifications, this will not fully apply for you, because if you apply this, then you run yourself into problem. But for single split residential development, this is still okay. You can still use it here and there. What this means is that for every 3 cubic meter, why I said 3 cubic meter is for 1. Okay, you know what I'm going to do? I will lay that out on card and send it to you just for explanation. But I'll try to explain it. Now, if you put yourself in one angle of your room and you measure 1 meter on the floor and 1 meter on the side, on in terms of length, and 1 meter in terms of breadth, and you raise your 1 meter off the ground, maybe to like below your window. You measure 1 meter below your window. That volume is going to be 1 cubic meter. I hope you understand. I hope you understand that clearly.
Yes.
So now, if you now raise it above by another 1 meter, then it will make 2 cubic meter of air. I hope you understand. Then if you now raise it to the top of your ceiling, by let's say your house is your internal building height is about 3 meters. If you raise it to that point again, then it's going to be 3 cubic meters. That's 3 cubic meter of air within that space. I hope you understand. So in essence, in explanation, this 0.189 cubic meter, kilowatts of cooling available for 1 square meter of floor space is also, like I said, as A is equals to B and B is equals to C. That is equally available for about 3 cubic meter of air volume within that space. I hope you understand. If you don't understand, we'll ask the questions later, then we explain it. So now, in essence, for every room, for every space in application, this average value of cooling is adequate in some application, not in all applications. So what that tells me is that if you have a room, for instance, look at the example, if you have a room, a space with a floor area of about 20 cubic meter, that's what you would just do in terms of specification on that will be that's 20 for every square meter. If a square meter requires 0.189 kilowatts, that means 20 square meter space would need about 0.120 times 0.189 kilowatts, which will give about 3.78 kilowatts of cooling required for that space. I hope you understand. I hope you understand that. So what this now means is for an example, if you have a room that is 20 square meters, okay, then you use this average to obtain a sized value of cooling capacity, an average value of cooling capacity. What it will tell you, for instance, if you convert 3.78 kilowatts, if you look at where does 3.78 kilowatts fall in this shelf capacities? We have 2.65, we have 3.50, then we have kilowatts, then we have 7.10 kilowatts. We have an average, a value here is 3.78 kilowatts, falls between 3.50 kilowatts and 5.64 kilowatts. So it is proper if you want to select a sized unit for this space to pick one of its 5 or a 5.6. But now the thing is, your 5.6 is way larger than your 3.7. Closer to your 3. So your selection 3.5 capacity unit for this. And what that clearly means. But that said in itself, that is as simple as that. But when I mentioned that the range does not apply in all applications, you see the thing is in a situation whereby you have double volumes, you have some spaces that have double volumes, or you have some spaces that have larger window exposures. Like for instance, let me use this in terms of explanation. rises in the east most of the time, except it has changed. Things are changing all over the world lately. This I don't know. But from what we learned in school, then the sun rises in the east and sets in the west. At midday, excuse me, the sun is usually right atop of buildings, atop of direct, how will I put that? A direct on point radiation in most parts of the country. But you would understand that the heat radiation from the sun between 9 in the morning and 12, that's 3 hours. But the heat radiation between 9 and 10 is considered as the heat radiation which is okay, permeable, or that is supposed to give you what do they call that vitamin? Vitamin D, yeah, which is still fairly okay. It's not too hot, neither is it too cold, but the radiation is moderate. That means that heat radiation between 9 and 10 is not giving, is not a very large or very disturbing heat generator. And but between 11 and 12, that's 1 hour of heat radiation. But in other on the other side, after 12, from 1 o'clock to 4 o'clock, you would understand that the heat radiation obtained from between 1 and 4, which is like 1 to 2 to 3 to 4, which is like 3 hours continuous heat, or even 5 sometimes. It gets that hot. It's about 4 hours of continuous heat radiation. At that point, not more heat load or any what the other. In some applications, one in business, in office, in glass, in multiple different style building material finishes. The applications need to be brought back to the design by first principle. I hope you understand. Some of this estimation might not work directly because air conditioning, the one thing you try not to do, no matter what you're designing, no matter what is expected to be designed, is that your air conditioning must not fail, because you have some buildings whereby they do not even, some of them don't even plan windows or extra levels of other kind of ventilations for it. They just go on and base it simply on air conditioning. So it is proper to design air conditioning such that it does not fail. When your air conditioning fails is when it is not providing as required cooling. It either is providing more than required cooling that is moderate and comfortable, or it is providing less. But for the purpose of this training for split systems, this unit, these values, that still works in some kinds of building applications, but not in all building applications. I need you to know that. So basically, we've been able to see that you can actually pick excuse me, use either of these average values to to design for to get your spec based on your floor area. I hope you understand lightly. So that's been done. I would bring a couple other things in terms of other types of split of apart from split systems, split air conditioning, other types of air conditioning systems. Excuse me. That are sorry, I need to get a little bit. Okay. Okay, now sorry. Other types of air conditioning systems, we have things like the multi-split unit, which is somewhat of the type I showed you earlier. This is a single split unit. This is a multi-split unit. I hope you understand. We have packaged units. Multi-split units are split units whereby you have maybe a single outdoor or multiple indoors in some cases based on specification and size. Then we have packaged units, which are composed units, composite units that have both the evaporator, condensers, everything combined into a single unit for use. Then we have the centralized unit, which has a large size, more design for more design applications and large air volume requirement. Then we have the air handling units, which are AHUs, whereby you have a central refrigeration point, a non-refrigeration, which I will sometimes call a specially modified split system, which in all these kinds of systems comes in different kinds of ways. They apply different levels of finishes as the case may be. The application are pronounced and they are special. They do not just, and the capacities are even far larger. They are not the kind of shelf life capacities some of the capacities are pre-designed and pre-installed, but they have very larger capacity. I think the max we had there, in most cases, it's about 24,000 BTU. I think you have some that are close to like 30,000 BTU before you now start talking about packaged free blows and the rest of it. Then we have rooftop units. Rooftop units are like specially modified AHU units, which are applied as single package systems. Then we have chilled water systems, which is another very special, which is another very special air conditioning system, which is used across. Then we have the fan coil units. Then we have the variable refrigerant systems, which are the variable refrigerant flow system. Those are some very deep, other deep sides of air conditioning design as case may be. But one thing I need you guys to understand quite well for single split applications is, in most cases, most of the sizes that you have, the specification comes in different forms. The specification comes in different capacities. But either of these items, the size of the cooling they can generate is extremely important. The size of the cooling, the size, the nature and arrangement of this also extremely. So I will quickly, so I won't forget, take you to a sample drawing, because some training is always as you talk about a lot of things, but I will so tell you there are some things that are coming into my mind right now which I can't start talking about now. I will so tell you that, but at least just to, because those some of them are they're very voluminous, but they are also part of the very important things you need to understand about air conditioning design. But this is just a pointer on things you would need in terms of this. I will go through a drawing quickly and try to do a quick relation of this. Can you guys see? Can you guys see this layout?
Yes, I can.
Yes.
You can see this layout.
Yes, you can.
Okay. I will just explain. This is a floor plan. Let me see if I can. Let me try to. Okay, this is a floor plan of a development somewhere in Lagos. We'll just talk lightly about it, because this will always also allow us um, to relate a lot more with some other items as it applies. Like one, for instance, the main air conditioning system applied here is single split. So I'm going to take this room, for example. I'm going to take this room, for example. This is a bed. In this space, it has the toilet area around here, the entrance to the toilet. It's one of the rooms in the flat space. So basically, from this, I think if you can see from the design, there's a specification already. There's a specification of the size of air conditioning, which is this. I hope you can see it. This is 5.65 kilowatt unit. I hope you can see this. That's 5.65 kilowatt unit, specified as a T1. Just as much as a 5.65 kilowatts. That means it's, if you look at this previous spec that we showed, that means in layman's language, it's a 2.0 HP unit. Then it's an 18,000 BTU per hour cooling capacity unit. That's what that shows us. But how did we come about this size of cooling? It's for the purpose of the training. How do we cover the size of cooling? It's taking one into consideration the volumetric the volumetrics, the size, the floor area, then the air volume of the space. That's what we applied to actually get this. But for instance, taking the floor area into consideration, I think when the floor area of this space was measured, let me see if I can pick that out up lightly. Okay, I think that was okay. The floor, the total floor area of this place, I think that's a special training on its own of this space. You know, you have his master bedroom. This is the entrance to the bedroom. Then you walk this way, this living area. Then there's a terrace here, so there's an enclosure here. What we consider at this point is the floor area of this space, of the room space. I think that's around about 29 square meters in all. So from that 29 square meters, we multiply that 29 square meters by 0.189 kilowatts, you will come to something around 5.4. I think it was like 5.4 or 5.5 kilowatts in terms of cooling kilowatts that will be required for this space. Then one other thing that is extremely important for air conditioning is location. You need to know how to locate properly, and how, because your location will determine your outdoor, it will determine the length of your piping, it will determine the quickness of your of removal of heat within the space, and it will also determine the effectiveness. Also, in that way, the effectiveness of cooling you will also get, because if the location is not proper, then you might have slight challenges. So, like for instance, one thing you should really look at for every space, it is not just about putting fixing air conditioning at any wall. Like for instance, if you look at this wall, this bed head, one thing you need to consider is the bed head. This is the bed head. Most people will sleep on this bed having their head around this space. If you sleep on this kind of bed arranged like this and your head is here, then maybe something is wrong, either with the bed or either with you. But in most cases, if you see a bed, you keep your head towards where the bed head is, not where on the opposite side of the bed head. So it is safe. Yeah, it is rather not safe for you to install your air conditioning at a point whereby it will have a direct blow on your bed head. It is not safe, because except you have a suicidal mission on whoever that owns a kind of apartment, then you can position your AC at a place that will go directly towards his head. It will just wake up one morning, they will call you that your client has turned into a block or something, a nice block of some sort. So your location is extremely important. You need to locate where it's proper, where it will not blow directly in the face of whosoever that is using the bed or using the bed, and locate at the point where you can achieve quick spatial cooling or quick spatial consumption within the space. Also, one thing you should try to understand in terms of air conditioning, if you look at this room space, we've talked about the capacities, obtaining the capacity. We have this capacity around. If you, in some cases, if you would understand that where the outdoor of this unit is on this terrace. I hope you understand. Except you are working with a ground floor or a first floor where you intend to hang the outdoor by the side or on one side of the wall. In most cases, which is not something which is generally acceptable lately. So you should position, it is ideal for you to position an air conditioner in such a space that you can easily drop your outdoors close to a place, very somewhere close, which is not too far, because there are limits to pipe lengthening and a couple of other things. Then one other thing we should also consider mainly is the drainage, the condensate, treating and managing the condensate from the AC system. Because in most cases, because people really do not consider some of those things from the onset, they install and they start having water damage issues every now and then. So it is always ideal. If you look at this drawing, there is a specification, there's a drainage pipe for this AC unit, this other one, which runs through this wall and finds a way to get out of the building. And it's not always ideal. You just dump your condensate out of the building. It will mess up virtually everywhere. So if you are doing a design, you do a design or you do an installation with such that you have provisions for every condensate coming out of every AC that can be taken into maybe into ground or into condensate manholes or into common drainage pipes that can actually get the water out of the system. Not that you're just dumping the water on the floor within the compound. That is not the neat thing to do. You have to have some level of aesthetical knowledge as also as you apply it to your engineering service in itself. So we've talked about Positioning is beautiful. You should try to get your positioning as much as you can in such a way that you have quick spatial cooling. Then also, in some cases, you might have to apply in this common room. Like if you look at this room, this is a very large room that has a single entry. If you enter this room, to the left, you have your space. You cover your cooling for a space in such a way that your unit can be. That's why you have them in split, simple uh, uh, miniature sizes. You have your specific unit to cover this space, and you have a separate unit to cover this space. Because what we have in all eventually is that you have an airflow coming in this direction. When it bounces back off this wall, when this space is fully composed of air, of cool air, it will blow in this direction. Then the second one too from this direction will blow in this direction over time. So you will have slight dead point at the entrance of the space on the immediate. I hope you understand. Then something you should also consider is your eventual cooling time, your eventual cooling time, your eventual airflow. You see, there's a lot to it. There's a lot to it in terms of design and rest, but we'll just push it out to this point because these are some of the basic for split systems. These are some of the basic things you should need to consider for split system. So in some of this specs will apply in most other cases. It will apply in most other cases, but you just need to apply understanding and discretion in application. And one thing you should try to understand, even with this level of small, this is just like a small level of knowledge. One thing you should try to understand is engineers need to have guts. You need to have guts and you need to use your discretion. Whether your discretion is going to kill you or is going to make you alive, you just need to use it, whether you like it or not. At one point, you will get to that point because your specifications must be on point. It must be right as it should be based on your own discretion. Though, yes, there are codes, there are standards that have been applied. We've not even talked about anything that has to do with indoor air quality. We have codes for indoor air quality. We have codes for indoor air, outdoor air volumes. We have codes for indoor spatial latent heat. Then and to understand about air conditioning. So for this is just a grant knowledge. It's a grant knowledge to you as based because of the lockdown. It's just grant knowledge to you for you to have a basic understanding of the split system and its applications and the variabilities as it may apply. So from this, I think I'm able to you have a little bit of understanding about what it's like. Obviously, you will have some questions. We'll be able to treat some questions in a short while. We'll be able to treat some questions in a short while. So from this, like I explained, this is a simple spatial example for a simple room. You have it. This other room has its own capacity. Then this living area has its own capacity, and this other living room has its own capacity, as the case. So it spreads around based on various capacity you can actually apply. Then in some other cases, you need to understand as well that these are single split systems. In residential development, you can equally use multi-split systems or even VRF system, as the case may be, but the design specifications and the design requirements will just be different from what you have for single split systems. Okay, so I think we'll stop we'll stop there for now. Then we'll take questions as the case may be. So